All right, our first example video for this section is going to be about matrix transformations. So just a reminder of what we talked about in class, transformations are essentially functions. You're going to be doing function transformations on x vectors in Rn, and we are going to use the fact that the transformation on that vector is the same thing as a matrix multiplication. Since x is in Rn, then A has to be an m by n, so that way when you take the m by n, you multiply it by the n by 1, your result is then an m by 1. And so your result is in Rm. Because n has n columns, and so the codomain of T is in Rm, or the points associated with the domain, okay, is going to be in Rm. All right, so let's look at this example here. I have an A, a U, a B, and a C, and it says that our transformation is going to take vectors in R2 and put them into R3. So let's think about what that means. That means U is in R2 because it's a 2 by 1. And if I take A and multiply it by that vector, I'm going to end up with something in R3. So let's look at part A. It says, find T of U, the image of U under the transformation T. Well, T U is equal to A times vector U. And so I'm going to multiply matrix A by vector U. And I'm going to do just normal matrix multiplication here. 1 times 2 plus -3 times -1. So I end up getting 4. Oh, 2. Just kidding. Sorry. 2 plus 3 is 5. All right. 6 minus 5 is 1, and -2 minus 7 gives us -9. All right, on part B, find an x whose image under T is B. That's the same thing as saying, do this, okay? So in algebra, this might be like, find the x value where the output is blank, okay? And you have to like backward solve for x. So we're essentially doing that exact same thing where we're going to set this up as a system and solve. So 1, 3, -1, -3, 5, 7. Let's augment that with B. I'm going to go ahead and do some row operations. -3 times row 1 back into row 2 ends up giving me 0, 14, and -7. And then row 1 plus row 3 back into there gives me 0, 4, -2. Notice that both the second and the third row factor down to 2 and -1. So you can basically just zero out this row and say that this is 2 and this is -1. And so what that tells me then is that x2 must be equal to -1/2. And if I plug that back in here, or you can do reverse, row reduction to get this into reduced row echelon form, you end up getting that x1 is 3/2. Okay, so that's going to be our answer for B, x1 equals 3/2. Now C says, is there more than one x whose image under T is B? And that is not going to happen because I found a unique solution for that. And so I only have one x. So is there more than one x? No. On D, determine if C is in the range of the transformation T. Well, the definition of range is that there is a linear combination in which it includes C. Okay, so if we were to augment, I'm going to have to erase some of this. So let's think about if there was a linear combination that contained C, then that means AX must be equal to C. Another way to think about this is like T of X equals C. So is there an X value in which this is true? Okay. So let's see if this is consistent. Let's see if we can figure this out. So 1, -3, 3, 5, -1, 7. And let's do that with C. Now, same row operations that we did before. So all of this ends up being the same, but not my output values. Let's see, I get -7 and 8. Okay, well now if I continue to factor this down a little bit, I don't end up getting something that does factor down. If I change this maybe to 1 and 2, and then I try to row reduce this around, I end up getting, once I do that, so I'm going to switch these. I'm going to make this will be a little bit easier. 0, 1, 2, where that 4, 8 was. 0, 14, -7. Okay, so if I do -14 times row 2 and add those, I end up with a 0 here and -35. So that's an inconsistent, right, matrix. So C is not, this can't be solved. So C is not in the range. Okay, let's look at a couple more examples. Example 2 is a very special type of matrix, okay? And what it does is it takes anything in R2 or in R3, excuse me, and puts it down on the x1, x2 plane. So it's still if you notice, it's still an R3 matrix over here, but it just drops out the last value. And the reason is look, you're going to be multiplying x3 by everything here all the time. So you end up like zeroing that out. So it doesn't necessarily change it to R2 space. Okay, it's still a 3 by 1 matrix, but it maps it so that it flattens down. There's another type of transformation that we can do called a shear transformation. And so you can see if you apply something like this with ones on the diagonal and then a 0 in the bottom, but then a number in the top, and you apply that to all the points on this graph, then it takes the points and it moves them. This ends up being 4, 2. Okay, so 0, 2, 0, 2 moves over to 4, 2. And so you can see like it just moves that piece over that way. Here's a better example, okay, if you want to look here. So this is the point, 0, 2. It moves it over to 4, 2. The point at 2, 2, when I apply this, so A times 2, 2, it ends up being 6, 2. So it like it's kind of, you can kind of see where it lays down, but it moves those pieces all over. It makes it kind of diagonal, which is a very interesting transformation from R2 into R2.